Now this one question which I am being asked often is, why do we study mathematics and what are its real life application? For me personally, mathematics is the language of creation. Everything that is happening around you, whether you see it or you don't, there is mathematics all around you, and it takes only a moment of flowing inspiration to realize it. In this video, we'll be studying one of the most important applications of mathematics in modern communication, which is cryptography, and in particular, we're going to talk about one-way function. Now, about 8 to 10 years back, I have published 2 research papers on cryptography, and one of which was one-way functions, and the other one was P versus NP. So in this video, we'll be studying one-way functions and their necessity for secured communication. Before studying one-way functions, let us study few basics of cryptography. Now in cryptography, suppose you are a sender who has some information which is to be transmitted to some receiver. Now we say this information is plain text. So the technical name for this information is plain text. Now what sender is going to do is, sender is going to use some tool to encrypt this plain text. And once this text is encrypted, it is called ciphertext. Now this ciphertext, it is being sent to the receiver, and then receiver is going to use some tool to decode or decrypt the ciphertext to plain text. So whatever coded information was sent by the sender is being received using encrypted systems. Now when we say cryptology tools, there are basically 2 kinds of encryptions that we use. One of them is symmetrical encryption or symmetrical key systems. And another one is asymmetric encryption or asymmetric key exchange. Now in cryptology, basically the tool that we use to encrypt or decrypt data is called a key. Now in symmetric systems, the key which is being used for encryption is the same key which is used for decryption or decoding. So both the keys, they are identical keys, they are same keys, and that's the reason we call it symmetric encryption. So the receiver and the sender, they'll both have the same keys. Now the sender is going to use this key to encrypt data, and then this ciphertext, it reaches the receiver, which again uses the same key to decrypt it back into the plain text. Now let us take a very simple example to understand this. Suppose we have a very simple message, say hi, which we want to send to the receiver in a secret way. Now here for an example, we are going to use a very basic encryption, which is letter number encryption or letter number cipher. Now in this encryption, A is 1, B is 2, C is 3 and Z is 26. So if we go in the same way, then H is 8 and I is 9. So this message hi, it's being encrypted to 89, which is our ciphertext, and this ciphertext is sent to the receiver. Now receiver again has the same key. Receiver knows this information that this is letter number cipher. So he's going to look at 8, which is H, and I, which is 9. So he is going to decode 89 as hi again. So this is a very basic example of symmetric key encryption. And the principal element here is the key which was used for encryption, which was letter number cipher, is the same key which was used for decryption. So we have used letter number cipher both for encryption as well as for decoding the ciphertext. Now in our communication systems, these very basic ciphers, they are not going to work. So basically in symmetric system encryption, we have something called as AES, which stands for Advanced Encryption Standard. Now what this AES does is, it takes the plain text, and what it does is it performs multiple rounds of encryption on this plain text. Now, without getting too much into detail, what AES actually does is it uses SPN structure. So SPN basically stands for substitution, permutation, and network. So what AES is going to do is it is going to transform data through multiple rounds of substitution and permutations using a secret key, and it provides a high level of security through its complex yet reversible encryption process. So we have this plain text. So our AES algorithm is going to perform multiple rounds of substitution and permutations using a secret key, and then this plain text will be converted into the ciphertext. And once we get this ciphertext, we are going to use the same AES encryption algorithm to reverse the process to again get the plain text from the ciphertext. Now in this case, the same AES algorithm, it is being used for both encryption as well as decryption, and that's why it is an example of symmetric encryption. And in symmetric encryption, AES is one of the most widely used encryption standard. Now to sum it up, sender is going to use AES key or AES encryption key to convert plain text into ciphertext. When this ciphertext is sent to the receiver is going to use the same algorithm or the same key to convert it back to the plain text. Now this AES 256 encryption is so complex and so secure that it is almost uncrackable using any known brute force method. So using the current computation technology and capabilities, it'll take millions of years to break it. So unless we have some substantial breakthrough in quantum computing, till then I think AES 256 encryption is here to stay. So very clearly, this is a very secure communication. Sender and receiver have the same key and no one else has access to that key. So if sender and receiver, they're connected to a very secure network which has no outside interaction and there is no chance of intercepting the key, then AES encryption is one of the best methods because it is fast, reliable, complex, and secure. Now the problem here arises when the communication has to be done over an insecure network, say for example over the internet. Now over this insecure channel, no one would be able to decode or decrypt this ciphertext unless they have the same symmetrical key. But the problem here is key exchange. How to exchange key over an insecure network or an insecure channel. Now over the insecure channel, without using any encryption, if you're going to share the key, it is very much likely that it could be intercepted, it could be hacked, and your entire communication could be compromised. So that is the problem we always had with symmetric key encryption. How to communicate or how to exchange keys over the insecure network. So unless there is a mechanism with which you can deliver the keys securely over this insecure network, this symmetric encryption has very limited use. You may generate symmetric keys, but then you will not be able to share it over this insecure or open channel. Now, solution to this problem was proposed in 1976 by two mathematicians, Diffie and Hellman, and they have proposed the idea of asymmetric encryption or asymmetric key exchange. And this, what they say is, rather than generating one key, we are going to generate two keys, one of which is a public key and the other one is going to be a private key. Now this public key will be known to all, but the private key is only known to the owner. They proposed a method in which this encryption is done by public key, which is known to everybody, but the message can only be decrypted or decoded by the person having the private key. And since we are using two separate keys, public and private keys, that's the reason we call it asymmetric encryption or asymmetric key exchange. Now the fundamental question is how to generate private and public keys. In order to generate two separate keys, a public key and a private key, they propose there should be a function which should be easy to compute in one direction. That is, if we have a value of x, we should be able to find a value of y very easily. But then for a given y, it should be nearly impossible to calculate the value of x. So if we have any such function where it is easy to find y from x, but almost impossible to find x from y, then we should be able to generate public and private keys, and they call such functions as one-way functions. So theoretically speaking, a one-way function is a mathematical function that is easy to compute in one direction, but it is impossible to calculate in the inverse direction. So informally, if we're going to say we have this function f, and this function f will be a one-way function if this function is publicly known. So everyone knows about this function, and for a given x, it is easy to compute fx in a polynomial time. Now we are not going to discuss polynomial time here, but for this function, for a given y, it is hard to find an x such that fx equals y. So precisely, even for the most efficient algorithm, the probability of finding the inverse in polynomial time should be negligible. Now, existence of one-way functions is an open conjecture. It has not been proved yet. If we can think and find or invent a function in which it is easy to calculate y from x, but impossible to calculate x from y, then you would not only prove the existence of one-way functions, but you will actually solve one of the classical millennium problem, P versus NP. Basically, there are 7 unsolved mathematical problems known as millennium prize problems, and one of the problem is P versus NP, and the Clay Mathematics Institute, they have announced this prize in 2000, and for the first correct solution of each problem, they are going to give you a prize of $1 million. Now till date, the only millennium prize problem that have been solved is the Poincare conjuncture. So this P versus NP is still out in the open, and one way of solving P versus NP is to prove that one-way functions exist. Now, even though existence of one-way function has not been proved, but there are many candidate functions which are close enough to be called one-way functions because the time and resources which are required to invert the functions is actually not feasible. Now, the question here is, once we have one-way functions, how do we generate private and public key using one-way functions? Now, since this function is publicly known, for a given value of x, it will be easy to calculate value of y. What Hellman-Diffie said, if we have a secret information or a trapdoor information, using that, we should be able to calculate the value of x from the value of y. One-way functions are also known as trapdoor functions. So using a trapdoor, we can generate a public key and a private key. Now, the first known application of this concept was done in 1977 by 3 mathematicians, Rivest, Shamir, and Edelman, and using their initials, they have formed RSA encryption or RSA algorithm. Now, in this RSA algorithm, what they have done is they have proposed a candidate function which is similar to one-way functions, and using that function, they have generated private key and public keys. Even though this algorithm was invented in 1977, it is still very much in use, though there are many people who now doubt the relevance and security of RSA algorithm. Now we'll study what RSA algorithm is or RSA encryption is and what is the mathematics behind it. For this, we'll take up an example. Now the key generation in RSA algorithm consists of 5 steps. So what we'll do is we'll go through each of these steps and simultaneously we'll take up an example so that we'll be able to understand, we should be able to understand how using a candidate function they were able to generate a public key and a private key. Now the first step in RSA algorithm is selection of prime numbers. So what we do is we generally choose two very large prime numbers, say P and Q, and we multiply these prime numbers to calculate their product, and we call this product as N. Now these prime numbers are so huge, generally they are either 1024 bits or 2048 bits. So their resulting product N, it is a very large number. Now for the sake of simplicity, we are going to choose very simple primes. So let P equals 5 and let us say Q is 11. So we have taken P as 5 and Q as 11. And again, I'll reiterate, in algorithm, we are not going to use simple numbers. We have to use very large primes, generally 1024 or 2048 bit primes, and not these simple numbers. Now 1024 bits has 2 to the power 1024 combinations, whereas 2048 has 2 to the power 2048 combinations possible. So with brute force, it is virtually impossible to figure out these prime numbers from the value of N. Now what we'll do is we'll multiply these two primes. So we'll multiply P and Q to find N. Now N in this case is 5 into 11, and which is 55. Now for RSA encryption as well as for many candidate one-way functions, the basic idea is for a very large number, it is almost impossible to find its prime factors. So for a given value of N, our assumption is no one will be able to figure out their prime factors. So from P and Q, we should be able to find N, but from N, we should not be able to find P and Q. Now to check if it is possible to figure out prime factorization of very large numbers, researchers used a supercomputer to simulate a quantum-based attack on RSA using Shor's algorithm. They find that to factor a composite number of 2048 bits, it would require around 10,000 qubits, 2.23 trillion quantum gates, and a quantum circuit depth of 1.8 trillion. If we have a super quantum computer, then that super quantum computer should be able to crack RSA in 104 days. Otherwise, the time and resources required to break N into prime factorization is unfeasible. So most of our modern day communication or encryption is based on this fact that it is impossible to break a very large number into two prime factors. Now the second step in RSA encryption is we are going to calculate Euler's totient function, and we write it as phi n, and this phi n is nothing but p minus 1 into q minus 1. Now p in this case is 5 and q is 11. So it will be 4 into 10, and that is 40. So we have this function phi n. This value is 40. And actually this function phi n, it is our trapdoor information, which we are going to realize in some time when we are going to use our private and public keys for encryption and decryption. Now n will be known to everyone, but then from n, we have already established it is impossible to calculate P and Q, and without P and Q, no one will be able to calculate Euler's totient function, which is basically P minus 1 into Q minus 1. And this value, it is our trapdoor information. Now the third step is we are going to select a public key or encryption key, and which we call it as E. Now the characteristic should be this E, it should lie between 1 and phi n, which in this case is 40, and this E, it should be co-prime to phi n. So this E, it should be co-prime to 40. So what we'll do is we'll choose E as some primes, let E be 7. Now this combination of N and E, it makes our public key. So our public key is going to be N comma E, and N in this case is 55 and E is 7. So this information is public, it is out in the open, so it is known to all, so everyone knows the value of N and everyone knows the value of E, but since they cannot factorize N, they will not be able to calculate phi n, which is our Euler's totient function, which is the basis of this entire encryption. Now we'll come to our fourth step, which is private key generation. Now basically this private key is, and let us say it is D. D stands for decryption, and basically this D is modular multiplicative inverse of E modulo phi n. So here we are using E. E is in public domain. Everyone knows E. Everyone knows N. The only person who will be able to calculate this private key D will be the one who knows this Euler's totient function phi n. And it is possible if and only if they know the value of P and Q. So we are going to generate this private key D, which is modular multiplicative inverse of E modulo phi n. So that is the reason this phi n is our trapdoor information. Unless we have the value of phi n, we will not be able to generate this private key D. Now, how do we calculate this D? Now, basically this D is equal to 1 plus k into phi n divided by E. Now, in order to find the value of D, we are going to use extended Euclidean algorithm. So what we'll do is, we'll write this as E into D plus K into phi n equals 1. Now here we know E is 7, phi n is 40. So we're going to write this as D into E plus K into phi n, and it is equal to GCD of E and phi n. Now since we have chosen E and phi n as co-primes, so this GCD, it is always going to be 1. So now we can write this as 7D plus K into 40, it is equal to 1. Now here we'll apply extended Euclidean algorithm. So we can write this 40 as 7 into 5 plus 5. Now we can write 7 as 5 into 1 plus 2. Now for this 5 we can write 5 equals 2 into 2 plus 1. Now since we need this 1 on the right hand side, we can write this 1 as 1 equals 5 minus 2 into 2. Now we'll put the value of 2 from the previous step. So this 2 is 7 minus 5. So we can write 5 minus 2 into 7 minus 5, which is 3 into 5 minus 2 into 7. Now before that we have this 5. So we'll take this 5 and we'll put this value here. So we can write 3 into 40 minus 7 into 5, or 5 into 7 minus 2 into 7. Now this is 3 into 40 and this is 15 and 2. So you'll minus 17 into 7 and this is equal to 1. Now here the problem is we should have plus sign here and minus sign with k. So what we'll do is we'll write this 17 as 40 minus 23. So we can write this as 3 into 40 minus, and then we'll write 40 minus 23 into 7. It is equal to 1. Now this is 3 into 40 minus 7 into 40. So there'll be minus 4 into 40 plus 23 into 7. And this is equal to 1. Now we can write this as 23 into 7 is 1 plus 4 into 40, or 27 is 1 plus 4 into 40 divided by 7. So which is of the form 1 plus k into phi n upon E. So now we have our private key D, which is 23. So value of D is 23, and only who knows phi n, which is our trapdoor information, they'll be able to calculate this private key D. It is impossible to find this D without knowing phi n. And this combination of n and D, it becomes our private key. So n is 55 and D is 23. So let us go through this key generation process again. We have chosen 2 primes, multiplied them to find n. Then using Euler's totient function, we have calculated phi n. Then we have chosen a public key E between 1 and phi n, such that it is prime to phi n. Then this n and E, it becomes our public key. And using modular multiplicative inverse of E modulo phi n, we have calculated the value of D from given value of n and E. Using extended Euclidean algorithm, we have calculated D equals 23, and it becomes our public key, which is ND, and now it becomes our private key, which is ND, and N is 55 and D is 23. So now we have two separate keys, a public key, which is 55.7, and a private key, 55.23. Now this public key, 55.7, it is known to everyone. It is open to all. Anyone and everyone will have an access to this public key, but this private key will be known only to the person having this trapdoor information, and generally it is the owner of private and public key. I know I've been reiterating this fact again and again, but then according to quintessentiallabs.com, it says it would take a classical computer around 300 trillion years to break a RSA 2048-bit encryption key, and according to LinkedIn, it would take approximately 19.8 quadrillion years to crack RSA 2048 using brute force. So basically this algorithm is unbreakable unless you either have an access to this trapdoor information or there's some technology in the future where prime factorization becomes simple. So now using RSA encryption, we have calculated our public key, which is 55.7, and we have also calculated our private key, which is 55.23. And this public key, it is known to all, but this private key, it is only known to us. Now, having generated public and private keys, now we'll look into the mathematics. How does asymmetric key encryption works? So let us take up an example. So suppose we have two users, Tom and Jerry, and they are connected through an insecure public channel, such as internet. Now, both the users, they're using asymmetric encryption. So both Tom and Jerry, they have their own sets of public keys and private keys. Now this public key, it is freely available. So Tom's public key, it is known to everyone, including Jerry. And in the same way, Jerry's public key is known to everybody, including Tom. Now we want to establish a secured communication between Tom and Jerry. And let us assume that in the previous example, using RSA algorithms, the keys that we have generated belongs to Jerry. So Jerry's public key is 55.7, where N is 55, E is 7, and his private key is 55.23, which is only known to Jerry. Now Jerry's public key, it is known to everyone, including Tom. Now Tom wants to send a message to Jerry, and Tom wants to send an encrypted message. So Tom has access to his public key, and suppose the message that Tom wants to deliver is M, and let us take a very simple message. Suppose this is number 2. Now this number 2 is the most guarded secret of the world, like Coca-Cola recipe. So this is our plain text. Now Tom is going to encrypt this message M using Jerry's public key using modular exponentiation. So we are going to generate a cipher text which is m to the power e mod n. So in this case, this C will be 2 to the power e is 7 and mod 55. So it will be 2 to the power 7 mod 55, and 2 to the power 7 is 128. 128 mod 55 is 18. So from this plain text m equals 2, we have created a cipher text which is 18, and we have done it using Jerry's public key, and this cipher text, it is being sent over this insecure channel to Jerry. Now this cipher text C equals 18 will be transmitted through insecure public channel. So it is accessible by all, but it will not make any sense unless they have Jerry's private key. Now Jerry is going to receive this cipher text which is C equals 18, and Jerry is going to start decryption using his private key which is 55 and 23. Now decryption formula is m equals C to the power d mod n. Now in this case, N is known to everyone. C may be intercepted because it is an open network, but no one has an access to D except for Jerry. So only Jerry will be able to decrypt this message. So now let us decrypt it. So this M, it is going to be C, which is 18. So it is 18 to the power and D is 23. So 18 to the power 23 modulo 55. Now we have to use modular exponentiation to calculate this. Now we can write this 23 as 16 plus 4 plus 2 plus 1. So there will be 18 to the power 1 plus 2 plus 4 plus 16. And we have to calculate its congruent value modulo 55. Now we'll start with 18 to the power 1. Now 18 to the power 1 is congruent to 18 modulo 55. 18 square, it is 324 and it is congruent to 49 modulo 55. 18 to the power 4. Now we are not going to use 324, we'll use 49 square. 2401 and it is congruent to 36 modulo 55. Now again we'll square it. 18 to the power 8 and that will be congruent to 36 square, and 36 square is 31 modulo 55, and finally we'll find 18 to the power 16. Now it will be this 31 square and 31 square will be 26 modulo 55. Now we have to calculate this M, which is 18 to the power 23 and which is congruent to this 18 to the power 1, 18 to the power 2, 18 to the power 4 and 18 to the power 16. So it will be this 18 into 49 into 36 into 26 modulo 55. Now we solve this. It is 825, 552 modulo 55, which is congruent to 2 modulo 55. So value of M is 2. So it is the same message which Tom has sent using Jerry's public key. Everyone knows N and everyone knows E. But without Euler's totient function, which is our trapdoor information, no one will be able to calculate D, and without D, it is impossible to decrypt this message. And that is the basis of RSA algorithm. Now we'll once again go through the steps of RSA encryption. So first, we'll select two primes. Then from their product, we'll find N. We'll calculate our trapdoor information phi N, and we'll select a public key E such that it is co-prime to phi N and it lies between 1 and phi N. And then using modular multiplicative inverse, we'll find the value of D. And this pair N and D, it becomes our private key. So we have generated two keys, NE, which is our public key, and ND, which is our private key. Now in order to send an encrypted message to Jerry, Tom need not have any secret information. Tom just needs an access to Jerry's public key, which is 55.7. And using Jerry's public key, Tom has encrypted his message and sent that message as a ciphertext. Only Jerry, who has his private key, that is, who has the access to N and D, will be able to decrypt it using modular exponentiation. And this is how asymmetric key communication or asymmetric encryption works. So this is the mathematics behind RSA encryption. Asymmetric encryption has solved the problem which was there in symmetric key, that is, the need to exchange the same or identical key. Here we just need to have two sets of keys, and therefore it is a very secure and reliable communication. Now, even though it has solved the problem, but then there are problems with asymmetric encryption also. It is fundamentally complex and it takes more time and consumes more resources, and therefore it is both time consuming as well as expensive. So here we have two things. We have symmetric key exchange, which is fast, but the problem is the key exchange. And then we have asymmetric key exchange, which is reliable and secure, but it is resource intensive as well as expensive. So in order to tackle both the problems, what we generally do is we use hybrid encryption, and for which we'll take up an example. So let us assume you have to access some information from Mathsmerizing.com. Now Mathsmerizing.com is a website which is being hosted on some server, and you are connected to that server through internet, which is an insecure public channel. Now you have your own public key and private key set, and Mathsmerizing.com server is going to have its own public and private key. Now for a secured communication, the first thing that you need to check is whether it is a secured website, and for it you need to check its web address. It should be HTTPS. So if you want to look at Mathsmerizing.com, there the address shows HTTPS, where this S stands for secure. That means the entire communication between you and Mathsmerizing.com is going to be an encrypted communication or a secured communication. Now, how are you going to access the information through Mathsmerizing.com? You're going to use either some browser or some app. Now, for an example, let us say you want to use Chrome as your browser. So you have your browser Chrome, with which you're going to access this website www.mathsmerizing.com. Now the first step is your browser is going to establish a connection with the Mathsmerizing.com server, and this connection is called handshake. Now generally this handshake is done through either TLS protocol or SSL protocol. So during this handshake, your browser sends hello client message to the server, where it tells the server which symmetric encryption standards and protocols it can support. Now after the initial handshake, knowing the browser's capability, the website server is going to choose the best encryption algorithm or best symmetric encryption algorithm, and it is going to generate a temporary symmetric key, which we call as session key. So it has generated a symmetric key, and we'll call it as session key or session symmetric key. Now this website server has generated a temporary session symmetric key, which is going to be used by both you and server for secured communication. Now this key, it needs to be exchanged. Now initially when you have established connection through TLS or SSL protocol, the website server, it has already sent its public key to your browser, and this key is contained within its SSL or TLS certificate, and these certificates, they are signed by Trusted Certificate Authority. So these certificates, they ascertain the validity or the integrity of website, that you are connected to a genuine website and not any fraudulent website. So your browser is already in possession of server's public key. Now server has to exchange symmetric key for communication to begin. Now server is going to encrypt this symmetric key using its private key, and it'll send it to your browser. And since your browser has an access to the server's public key, it can decrypt the information using server's public key. So using server's public key, Chrome now will have the session symmetric key. So now both your browser as well as the web server, they have same session symmetric key. Now the communication can happen between them using symmetric encryption. So in this case, we have used both asymmetric key encryption as well as symmetric key encryption. Asymmetric key encryption is used to exchange the symmetric key, and the entire communication is conducted through symmetric encryption. So this is your hybrid model where we would use both asymmetric as well as symmetric encryption. And once the session is terminated, the server is going to delete this session key, And what it will ascertain is if in future someone hacks into the server, they will no longer have an access to this symmetric key. So whatever information is there on the server which is related to you will not be accessible to any hacker. So this is how we use hybrid encryption. This hybrid encryption is used in almost all the encryption standards. Now almost everyone is using WhatsApp. Now WhatsApp claims end-to-end encryption. Now whenever someone installs WhatsApp on their device, it automatically generates two keys, a private key and a public key. So all the WhatsApp users will have their own combination of public key and private key. Now public key of all the users will be known to each other. Whenever they establish communication between them, their public keys will be exchanged and their private keys will be stored only on their own personal device. Now suppose there are two people, Sherlock Holmes and Dr. Watson, and suppose Sherlock Holmes has to transfer a secret information to Dr. Watson. So now he's going to use WhatsApp. So what he's going to do is, since he has an access to Dr. Watson's public key, Sherlock Holmes is going to encrypt the message using Watson's public key, and this encrypted ciphertext will go to WhatsApp server. Now WhatsApp server, it doesn't have anyone's private key. So whatever ciphertext or encrypted information Sherlock Holmes is sending to WhatsApp server, it cannot be decoded at the server's end. What server is going to do is, server is going to relay that information or that ciphertext to Dr. Watson, and Dr. Watson using his private key can decrypt the message. So in this entire communication, only the public keys are being exchanged and private keys are stored only on the devices, end-to-end devices, and not on the WhatsApp server. Encryption is happening at Sherlock Holmes' device and decryption is happening at Dr. Watson's device, and WhatsApp server is only relaying the encrypted ciphertext, and the server itself has no access to private key of either of the users. So that's why it is called end-to-end encryption. And to make the process more safe and secure, what WhatsApp periodically does is it changes the private and public key combinations. So it periodically changes the keys so that it makes the entire encryption much more reliable and secure. So basically, this is the mathematics behind modern day communication. Without one-way functions, or to be very precise, candidate one-way functions, modern communication will not be possible. Now there are some more topics which are related to one-way functions, and few of them are digital certificates, hash functions or hashing functions, which are currently being very much used for storing passwords as well as in blockchain technology. So maybe in future, I'm going to make some video regarding that. So for now, this is it. Take care. God bless you.